Joining us today on Superheroes of Science, we are so happy to welcome Deva Chan. Deva is an assistant professor in the Weldon School of Biomedical Engineering here at Purdue University. So welcome.
Thank you. I'm very happy to be here, and thank you for the invitation to talk to everyone.
We certainly appreciate you taking the time, and we're very excited about it because it's as we had spoke beforehand. There, we had found you, and we were looking up MRI things, and we thought, well, it's we know people's had MRIs. I mean, heck, I've had a few, and I really don't know if I know much more than the fact that I've had them. And so I thought this would be a really good thing to just kind of educate everybody and let people know a little bit more. But it seems like when Sarah introduced you as biomedical engineering, the School of Biomedical Engineering, there's it's like you couldn't decide on just engineering or just medical or just bio. You just had to do it all.
Yeah. Well, actually, it turns out that when I started my undergraduate studies, I was initially gunning for pre-med. And then I realized, I was an engineering major at the time, and I really enjoyed working with my hands and actually designing things and working out problems. And these were things that I thought I could better approach as an engineer rather than, maybe a doctor in private practice. And so I ended up going that direction, doing research and, making new devices in order to get my research done, which gave me the hands-on part of it. And then also doing research on the biomedicine side, where, hopefully the things that we discover in my laboratory will eventually be able to help patients down the line. Or at least give us a better understanding of how the human body works, right? Because it's such an intricate machine, and that's sort of, as a bioengineer, I guess the part of the human body that you can sort of see as this beautiful machine is really fascinating to me.
I like that. That's really cool, and it's just amazing. I mean, we don't even think about that sometimes. The fact that you have to understand medicine, you have to understand the body, and you have to understand engineering to be able to make these things that helps us.
Right. I was just thinking you kind of have like the best of all those fields. Like you started thinking maybe pre-med, and then you think, well, I can do this too, and I like designing things, and it's like the best of all the worlds.
Yeah, I feel like I really found a home in biomedical engineering because it lets me do a lot of the things that I like to do, and it still lets me challenge myself because there are so many unknowns. Every day is interesting. We're finding new things, and we're finding new obstacles to finding out those new things. And so it's always interesting, and it's different every single day, and it's kind of refreshing every day because of that.
So MRI, what's MRI? How does that play into what you're doing?
Yeah, so MRI is a medical imaging modality, and that's actually a technology that enables doctors and researchers like myself to be able to see inside the body. And Purdue is actually very, very well established in terms of MRI technology because we have multiple MRI scanners on campus for research use. And so most places you have an MRI that you have to use at a hospital, and researchers on the university campus have to sneak in after hours in order to be able to use it. And we actually have 2 research dedicated human MRI scanners, which allows us to be able to do studies on different platforms on campus. And that allows us to be able to make lots of impact in things like studying neuroscience and what I study, which is musculoskeletal disease.
Oh, well, so I don't know. At first, I imagined you just grabbing a grad student and throwing in there, saying, "Hey, we need to test this today." But I'm guessing it's a little more to it than that.
Yeah, sometimes we do throw the grad student in there, right? Or the grad student throws us in there in order to test out some scans. But there's actually, in terms of human research, there's actually this long process that we have to go through to make sure everything is safe and that the studies that we're doing are important and will actually give us good information, and that the benefits for anybody participating in the study are actually much greater than any potential risks. And we do really good job in terms of making sure that anyone that volunteers for these studies to help out science is also very minimally at risk, if at all.
Mm-hmm. Well, I really want to ask about the variables that you're looking at, but I think before we get there, we probably need to find out a little bit how it works.
Yeah, definitely. And I've luckily prepared some visuals for those of you watching at home. Again, for those of you listening, I've been asked to describe everything. So hopefully my ability to describe things in words is also as good on the podcast version. So let me bring this up right now. CDC that describes how the incidence of arthritis is really increasing as the population of the United States is growing. And so somewhere before 2005, 46 million people had arthritis. And in the year 2020, it's projected that 63 million people have osteoarthritis. And if we project 20 years more in the future, it goes up to 78 million. And so obviously this problem of arthritis is going to be a huge one in the decades ahead. And so how do we fix arthritis? And also, why do we use MRI to study arthritis? So to give you a little bit of perspective, I'm starting here with this picture of the healthy joint. You have bone and cartilage and ligaments and all these other tissues inside the knee that are nice and healthy and enable people to walk and move and run, go upstairs, all without pain. Unfortunately, when you have a disease like osteoarthritis, you start getting a lot of damage in these tissues. And there's a lot of different risk factors that lead into osteoarthritis. Some of these are related to genetics or deformities in the joint. Some of them are just based on higher risk demographics or changes in the biomechanics of the joint or how the joint moves. And then finally, there's some things that we might be able to control, but not entirely. And these include obesity, overuse of the joint, as well as any joint injuries. And my lab really focuses in on the joint injury, because when you have a joint injury, you kind of know a single time point where you might be predisposing yourself to getting osteoarthritis. And so what we want to know is, how do we understand these early changes in osteoarthritis, or OA? And also, can we go back? And one of the tools that we use to understand these early changes in in osteoarthritis is MRI, which is magnetic resonance imaging. And so now we get to the fun part where I talk about what MRI actually is and try to explain to you how a little bit of it works. So what is MRI? Here I show just one of the scanners that we actually have on campus that's available for research, and it fits a human. And you can sort of see, let me turn on, I'll start this slide over again once I figure out how to get this pointer to work. There we go. Okay. And so what is MRI exactly? So I'm showing here a picture of a scanner that we have on campus, and you can see this really large scanner. It's this big circle, it looks like a tube, and that's actually the superconducting magnet. And the patient or the subject lies on this gantry, and then when they go inside for a scan, there's a lot of things that happen. And so for a little bit of perspective on what MRI actually is, it stands for magnetic resonance imaging. And to give you a little perspective on how strong of a magnet we're really talking about, the Earth's magnetic field ranges from 25 to 65 microtesla. Now remember that I just said microtesla, because in typical hospitals, the MRIs have a strength of 1.5 to 3 Tesla. So what does this all mean? So a microtesla is actually 0.000001 Tesla, right? So six zeros essentially, right? 10 to the minus 6 Tesla. And that means that 1.5 to 3 Tesla, which is what the MRIs are in the hospitals, is actually 1.5 to 3 million microtesla. So that's about 94,000 times stronger than the magnetic field of our Earth, right? So it's a pretty big and strong magnet. Also, it's a hefty machine. It weighs about 5.5 to 8 tons. And a lot of that weight is actually because it has to contain liquid helium. And you need the liquid helium because you have to cool the superconducting magnet down to 4.15 Kelvin, right? And that's really, 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 really cold. It's equivalent to minus 269 degrees Celsius, or about minus 452 degrees Fahrenheit, right? And going back to the weight of this MRI, 7.5 to 8 tons is about the weight of an adult male African elephant, which is one of the largest land animals that we are aware of, right? And so this is a huge machine. It has to have a huge magnet. But what exactly does it do, right? And so the whole concept of MRI is that it uses this phenomenon called nuclear magnetic resonance in order to generate images. And so there's 4 critical parts of an MRI system. The first one we've already talked about, which is the superconducting magnet. It is always on, and it has to stay on because it's really hard to get all that temperature down to 4-point-something Kelvin. There's another set of equipment called the gradient magnets, and turning on and off these gradient magnets actually helps to be able to change the magnetic field in very small ways. It tweaks the magnetic field inside the scanner so that you can manipulate the magnetic field. Next, there's a set of equipment called the radio frequency coils, and these are the components that actually transmit and receive radio frequency signals. And we'll talk about that more for sure. And then lastly, of course, everything involves computers, right? So there's a computer that interprets the signal that comes out of the MRI system and uses that to generate images. And so all of this is done, obviously, in a patient or a tissue or something like that. And so let's talk a little bit more about how MRI works, right? And so this is a picture of me before MRI. And this is a picture of me after MRI, right? And so on the right, we actually see an MRI of my brain. And you know, it's just the standard anatomic image, and it allows you to be able to visualize some of the morphology of the tissues. So the shape of these tissues inside my body. And so there's this entire field of research that actually goes into how to optimize the best image for the different kinds of tissues that you're interested in. And we're not really going to go into that today, but I do want to explain a little bit about the so-called classic model of understanding how MRI signals are generated. And so in order to do that, we're going to focus on a super, super tiny part of my brain or any tissue that is made up of just a handful of molecules, right? And so it makes up less than a pixel in this image that we see on the right, but it's a good way to visualize what's going on. And so inside this tissue, we have this tiny area that's filled with a lot of molecules. And these molecules are made up of different nuclei, right? And so different elements make up different molecules. And the element that MRIs in most hospitals use the most is hydrogen. So it actually looks for the protons in all of these different molecules. And so these protons or hydrogen nuclei are really abundant in our body, right? And so what I'm showing here is just a graphic of different protons in a small area. And they have a lot of random alignment. They're just they're just nuclei floating around inside this tissue, and they're oriented in different directions when there's no magnetic field. And so when we put a magnetic field on, or we put a patient inside the MRI scanner, these protons feel this intense magnetic field that is 94,000 times that of the magnetic field of Earth, and they suddenly align, right? And so you'll see on this visual that the protons are mostly aligned in the direction of the magnetic field. And if you look very carefully, there's actually some protons that are not aligned. They're actually aligned in the direction of the magnetic field, but they're pointed in the opposite direction. And the ones that are pointed in the opposite direction have to try harder, essentially, to get to that place. And that means that they are high energy protons. And all the protons that are lined up with the magnetic field are these low energy protons. And of course, because they are low energy protons, you can actually do something to get them to a higher energy level. And that's how magnetic resonance imaging begins to be able to generate these signals. And so when we do that, we actually use the radio transmission, the radio frequency coil that we had. And so we turn this radio transmission on, and what that does is that it excites these protons that are in low energy levels, and it actually flips them a certain amount with respect to that main magnetic field. And so now on this screen, what we see is that all these low energy protons that used to be aligned with the main magnetic field are now misaligned with that main magnetic field. And so they're off kilter essentially. And so when this RF pulse gets turned on, this radio frequency pulse gets turned on, all these protons that used to be low energy now have a slightly higher energy level, and they're tipped away from that main magnetic field. And so what happens next is that you then turn that radio transmission off. All of these protons are still lined up a kilter from the main magnetic field, but now they want to realign. And so what happens is that you have this signal that's generated when these protons move back into place. And that's this process called induction. And in the technical speak, this produces a signal called the free induction decay. And that's a signal that's measured by those radio frequency coils that receive signal. And so this is what happens. The protons move back into alignment with the main magnetic field. They generate a signal, which is then recorded by our computer. And so what's interesting with how MRI works is that how quickly these protons relax or move back in alignment with the magnetic field actually tells us something about the proton's surroundings as well. And so a proton that's attached to a water molecule will relax in a very different way from something attached to a sugar molecule or a fat molecule. And that allows researchers and scientists and doctors to be able to distinguish between different types of protons as well with MRI. So that's another really cool feature of MRI. And so now that we've turned off the radio frequency, we've had that signal induction, we go back to this main magnetic field. And so all these protons line back up with the magnetic field. And at this point, we're thinking, okay, well, if there's only a certain number of protons on the screen, right, in our bodies, why do we even need 1.5 Tesla versus 3 Tesla versus 10 plus Tesla, which is currently the strongest magnet that they have out there for human use? It's only available for research use, of course. It's not FDA approved for hospitals yet. And the reason for that is actually because the more strong of a magnetic field you have, the more nuclei you have that align with the magnetic field instead of against the magnetic field. And as we saw, the more that you have aligned to the magnetic field in that low energy state means that you have now more protons that you can excite and get signals from. So you actually get more signal coming from a stronger magnetic field. And so that's why the 3 Tesla is better in terms of giving you signal than the 1.5 Tesla. And there's this constant innovation in terms of trying to get stronger magnets into hospitals. And so finally, we said that all the signal goes to a computer, right? And so this computer takes this induction signal, which actually looks like what you see on the left here. And for those of you that aren't on a screen, this is basically a black image with a splotch of white and gray interdispersed, right? So it's not really the image of my brain that we kind of saw, a few minutes earlier. And this is because the signal that it takes from these protons is actually in what's called K-space. And that means that it measures the frequency of these induced signals rather than just their location. And so you require a computer to be able to interpret all this information. It actually goes through a mathematical algorithm called an inverse Fourier transform. And then you are able to so-called reconstruct this image of the anatomy. And so at the end of the day, you finally get our anatomy image rather than this splotchy image of white and gray on a black background that you have on the left. So voila, we need math, we need physics, and also we need a good understanding of the chemistry of these protons in order to understand what kind of quality signal we're getting from there. And so in my research, what does an MRI tell us? I do musculoskeletal research, so at the bare minimum, what it tells us is where you might have an injury. And so here I have different images of the knee. On the left, in the middle, it's the cervical spine, so the spine in our neck, and on the right, it's our ankle. And in each of these images, you can see locations where you have hyperintensity or a lot of brightness where you shouldn't have, or you can see morphologic changes, so changes in the shape of the spine in the middle. And then on the right, we see just a change in overall appearance of one of the ligaments in the ankle. And that tells us, and that tells doctors especially, where the source of pain might be, where the injury might actually exist, and what it actually looks like in 3D. Of course, MRI isn't just used in the musculoskeletal system. There's really cool ways of using it in other systems as well. And one of these is in the cardiovascular system. And so you can use chemicals called contrast agents, and you can inject them, and that will actually help to metaphorically light up the blood vessels. And so on the left, we see an image of a person's neck and upper back. And you can actually see that after the contrast injection, you can see where these blood vessels actually lead. And so you can track it from the heart all the way up through the carotid to the brain. And that enables doctors to be able to see where you might have occluded arteries, right, or blockages in the arteries. On the right, what we see is what's called a cine MRI. And that's actually just a movie made of MRI frames. And here we see a beating heart because you can take an image throughout the cardiac cycle and be able to piece together what the heart might look like and what the blood vessels might look like and the blood in the heart looks like during a heartbeat. And so that's another cool way that doctors and scientists use to both study the heart and the cardiovascular system, as well as try to figure out what might be wrong with a patient. And finally, I did mention that there's tons of innovation consistently going on with MRI, and one of the more cool things that you can do with it is this technique called diffusion tensor imaging. Now, it's not only used in the brain, but in the brain, it gives you this unique feature where you can track where water molecules actually want to travel inside the brain. And that means that since water wants to travel in the direction of neurons in the brain, that you can actually track neuronal tracks inside the brain. So you can see where connections are formed inside the brain by neurons. And so on the left, we have some of these mappings of our neural tracks superimposed on top of just a single image of the brain. And on the right, we have this composite image through a different part of the brain that tells us not only where you might have alignment of tissues like axons and neurons, the axons of neurons rather, but it also what direction those things point. And so again, this is used not so much in the clinic right now, but definitely in research to better understand how our brain works. And that's kind of that final frontier of understanding how our bodies and our minds work, is trying to understand the brain. And so MRI overall, I think, is a really cool technique to be able to use in both research and in hospitals to learn more about our bodies and how to keep our bodies healthy, and also to how to prevent and cure diseases.
Wow. That is so cool. It's so many questions come to mind. But first, when you talk, it's using a magnetic field, and then we're using radio frequencies. With those being the two inputs for that, and a common misconception a lot of people have is it uses some sort of radiation.
Right.
Those two are non-ionizing radiation, so there's no way you can get cancer from it or something like that based on what you're using at all, right?
Yeah, as opposed to techniques like X-ray or X-ray computed tomography or CAT, right? CT scans or CAT scans. There's no ionizing radiation that you have to worry about. And so, for the techs that work there, they don't have to protect themselves because they're exposed all day. And for the patients that are exposed inside the system, they don't have to worry about things like X-rays passing through their body.
Mm-hmm. I think it's a fairly common misconception that people just don't understand how they work, and so they assume everything is like an X-ray.
When you had mentioned several times, and I just wanted to clarify in case people were listening and maybe thought one way and not another, but you talk a lot about nuclei, and then about protons, like hydrogen protons. So when you were speaking about nuclei, because I'm thinking it's the body too, is it right that it's the nuclei in atoms, or are we speaking about cellular nuclei?
Oh, yeah, of course. So this is definitely one of those things you want to clear up, right? Because in biomedical engineering, one of those brilliant things about being in multiple fields where things intersect is that you have the same term can mean very different things in two different fields. And so yes, in this case, we are definitely talking about the nuclei inside atoms, right? And so you have the nuclei and you also have the electrons that make up the atom. We're talking about the nuclei in those atoms, and these atoms make up the molecules that make up the at several levels higher, make up the tissues in our body.
And then I was thinking too, I was listening to the size and just the, just the mass of instruments like this. Does it take special materials? And I'm assuming these are probably set up in basements, or, I mean, does concrete support something like that? Or does it need to be supported on different surfaces?
Yeah, so concrete will do a good job, but you need to make sure that it's thick enough. And I'm sure you can talk to building engineers all day about all the different requirements. But usually, yeah, these are in basements, which is usually why they're in the basement of hospitals, or on the very first floor if there isn't a basement. And that's, for multiple reasons. The biggest one is the weight. But you also don't want to worry about vibrations or other things that might affect your images.
So that's a great point too. So then like vibrations outside of the machine, would it be sensitive to those?
It's not necessarily too sensitive to things outside because it's such a huge machine, but vibrations that might be caused by the magnet could then affect other people as well, right? So if you're in a hospital and you have sensitive instruments that you might need for something else, you don't want this too close as well, because you have a strong magnetic field and that can affect other electrical equipment, right? So if you're in a hospital, they'll warn you if you have a pacemaker that you shouldn't get near it. You shouldn't get past what's this so-called 5 Gauss line. And that's where the magnetic field becomes too strong for, people that might have metal implants that are magnetic, or people that have pacemakers or rely on other electrical equipment. You definitely don't want to bring your cell phone anywhere near it.
Oh.
It'd be a bad day to leave that in your pocket, huh?
Yeah.
What about
credit cards, definitely take those out, right? I tend to leave my wallet, my phone, everything that's metal, that's magnetic, that's on me. I tend to leave them outside in the scan room where the computer is, before I go in with a patient or any kind of tissues that I want to scan in the room that houses the MRI scanner.
Yeah. Wow.
What's the distance for that drop off? And
so it actually differs depending on the strength of the magnet, right? And so the drop off isn't linear, which means you can't just draw a line and assume that the further away you are, the less it is proportionally. And so depending on the manufacturer and the magnet and its configuration, it can be very, very close, which is the case for some really high field research only magnets for scanning small animals like mice. Or it could require an entirely different room, like the MRI scanners that are often used in hospitals, because those are just much bigger magnets.
That is so cool. I did not realize there was a radio frequency transmission in there for an offset, and then it would work off of inductance. I had not thought about that. I guess
showing that graphic of how they align and then turning that on and having them misalign. I just love that. And I love talking about the difference between the low energy and the high energy nuclei, and how you try to, manipulate those low energy ones, and then
you kind of give them a little boost with the radio frequency, right? And so and so what it does is it sort of just excites it to a level that it has its own energy now and wants to go back to this low energy state, and that causes that induction.
Yeah, that is cool.
That is cool. I wouldn't have thought of it. It's you see it, inductive chargers and stuff like that. I just didn't realize we were using it for so long.
Yeah.
How long has MRI been around about, do you know?
Oh my gosh, definitely at least since the 50s, but it took a long time to really go from this idea that you could use nuclear magnetic resonance as as a method, to being able to use it in images, to being able to develop all these different ways of getting good images out of it.
Now, and that brings up a question too that I had. As soon as I saw I think it was even the first slide you had where it said nuclear magnetic. What do we mean by nuclear in this case? Because when you say nuclear, I'm thinking like nuclear power plant, radiation, and stuff like that.
Right, you tend to think of radiation,
Oh,
and that's actually why they removed the word nuclear from nuclear magnetic resonance imaging, because that's what it was known as very early on. And, you know, obviously in the 50s and 60s, that was probably not the best name for a new medical technique to call anything nuclear. But the nuclear actually refers to these protons or other nuclei that you can excite. And so for all of nuclear magnetic resonance imaging, you can think of all these nuclei as tiny little magnets that move around inside this really big magnet, right? They either line up with or against, and then when they move and they move back, they induce that charge because it's a magnet moving inside another, moving inside a magnetic field.
I like that. I like that explanation and stuff. Often things sometimes certain words just immediately trigger people. And, you know, if you're talking about nuclear medicine, you're like, oh my gosh, they're radiating me. And I'm going to become, I don't know, the next Incredible Hulk. It's the gamma radiation or something. But no such luck on Incredible Hulk, and no radiation.
Yeah, we haven't quite gotten there with gamma ray technology yet to get to Bruce Banner.
Yeah, he was really ahead of his time, wasn't he? But okay, awesome. You're definitely the first first guest we've ever had that showed us an image of their brain.
Yes, this is very exciting.
Not too many people have an image of their own brain, I guess, to be fair.
And it didn't look, I've never seen an MRI picture, but if you're watching the video, the picture did not look like how I thought an MRI. I don't know what I thought MRI would look like, but it just looked different than how I thought it would. I think I could see the parts are really well defined, and I guess I wasn't expecting that level of definition.
And how is that the end product different than an X-ray?
So there's a couple of things, right? So X-ray, it relies on X-rays just passing through the body. And so what you get is called a projection image, right? So it passes through, these X-rays pass through every single tissue along the way. And when you see that final image, it gives you a signal that's proportional to every single tissue that passes along the way. And so if you have this large thing that blocks X-rays, like a metal implant or even bone sometimes, then you can't see the soft tissues that are next to it. And that's where MRI really excels, is being able to see these soft tissues, because soft tissues have a lot of water, which means they have a lot of protons, and that means they have a lot of MRI signal. And so one of the ways that MRI is different from X-ray is just the fact that it produces the signal in a different way. And it also allows you to produce a volumetric image, right? And so instead of a projection, which just goes through all of the tissues and sort of flattens all these tissues into the same 2D image, you are able to go what's called slice by slice through the body. And so you can have different planes of imaging. So you can take an image at the very top of the head and go all the way down to the very bottom of the brainstem in order to look at the full brain and not just a 2D flattened out image of the brain.
That is awesome. That is awesome. We appreciate you explaining like the reason or part of the reasons you're researching it now, being with like the arthritis and things. It's really kind of nice to know what people are doing. Now, when you're researching yourself, I realize I'm deviating a little bit from the MRI now. I'm going back to you, but when you do research, are you looking at, because you mentioned the arthritis that your group was working on and stuff, are you also looking at how the technology itself works and making comments, suggestions, or questions about ways of changing an MRI type technology, or is it simply a tool that you're using for your research stuff?
Yeah, so we actually do a little bit of both. Once a technique is developed, right, we don't discriminate between the techniques that we develop versus what everybody else uses if it can give us more information about a healthy or an arthritic joint. So we definitely do a lot of applications-based research. But there's always going to be needs that we end up encountering where the current technology just isn't able to do it. And there we either work within our own team or we collaborate with others to develop either new techniques or develop ways of tweaking current techniques that will give us better resolution, so better ability to see smaller things, or a better temporal resolution, right? So with the image of the heart, if you can do more frames per second, then you can actually see more of what's going on in really quickly moving tissues. And so there's two different ways there. You can increase your resolution, but there's also different ways that you can tweak the contrast of the images or take advantage of the relaxation of these protons and actually do what's called relaxometry. And you're actually doing multiple images that let you know how the pixels in every part of your image, how they on average relax with respect to the magnetic field. And that map actually tells you how much tissue damage you might have in cartilage, for example.
Wow, very nice.
Yeah.
Well, thank you for your time. This has been very enlightening. And selfishly, I just really appreciated this because it's like it wasn't too long ago and I had an MRI because of an injury. And I remember being so curious about how does this thing actually work and what's happening there. And so selfishly, I really, really appreciate you taking your time. But professionally, we also obviously appreciate getting the word out and letting other people know how it works. And thank you.
Yeah, absolutely. I really enjoyed just, talking about it and I like to teach others about just how engineering works and different aspects of engineering. So thanks to both of you for giving me this chance to share our stuff.